Hello everyone, my name is Bohan Wu. I'm a physics PhD student in the University of Arizona. Today I'm going to talk about a quantum computing architecture in a scalable photonic platform. We posted our research result in arXiv. If you are interested in, feel free to check it out. Let me start off by filling you in on the background of this study. Quantum computing is a very hot research topic in recent years because it is widely believed to solve the intractable problems for classical computers. For example, factorization problem or data searching problem. You might wonder, what kind of quantum computing system can we choose? A research team in Google published their breakthrough result recently about quantum computing. They use the system of superconducting qubit. The system is gate-based, which means the computation operation requires high-fidelity gate. However, in experiment, it is very challenging to realize the gate with high fidelity. There is an alternative solution, which is called one-way quantum computing. How does that work? First of all, we need to prepare large-scale cluster state. Cluster state is a specific type of multipartite entangled state, which can persist the entanglement under the measurement. Secondly, we need to do a single qubit measurement to the prepared cluster state. Finally, we do the feed forward. So the idea is, if we do a single qubit measurement plus feed forward to the prepared cluster state, it is equivalent to have a gate operation in the output, so we can bypass the need of high-fidelity gate. But how do we generate large-scale cluster state in experiment? Two research teams published their experimental result recently about generating large-scale cluster state. Both of them use a bulk optical system to deterministically generate two-dimensional CV cluster state. In CV cluster state, they encode the quantum information in optical bosonic modes. However, in general, bulk optical system requires a lot of optical components in a single optical table, for example, in this picture. So in terms of scalability and mass producibility, it is very challenging. So I'm wondering, is there any possibility that we can miniaturize the whole optical system on a single chip? If we can do so, we got some benefits. First of all, this integrated photonic platform is compatible with current CMOS technology. Also, this platform has high scalability and portability. Finally, the system is relatively robust. In order to do such research, we need the knowledge of quantum optics and the techniques of nanophotonics. In our research, we fabricate the ring resonator and waveguide on the chip. The chip is made by the material of silicon nitride. We send a pump light whose optical power is below the cavity threshold into the waveguide into the ring. The ring resonator can be regarded as a cavity, so when the pump field goes into the ring, its optical power will be enhanced, so the material nonlinear response becomes significant, and a nonlinear process called four-way mixing takes part. In this process, two pump photons are converted into signal and Euler photon. As we can see in the cartoon figure of the output spectrum, a bunch of signal Euler photons are generated. Also, we can mathematically prove that signal and Euler photons are entangled. After we generate a bunch of signal Euler photon pairs, we can optimize the squeezing level by changing different physical parameters. For example, in this figure, we change different aspect ratios of the waveguide. And optimally, we can generate more than 2,000 entangled spectral modes. After we generate the non-classical resource on the chip, we need to figure out how to coherently detect the thousands of entangled spectral modes. We can do so by preparing another ring resonator, but this time we pump it above the threshold and lock the phase of each spectral mode. It turns out we can generate an optical soliton on the ring. There are some papers which talk about how to use ring resonator to generate optical soliton. The below figure shows our simulation result of our soliton spectrum. With the generation of optical soliton, we can use it to coherently address the corresponding entangled spectral modes. To generate one-dimensional CV cluster state, we need two identical ring resonators and pump them at different modes. Afterwards, we use a beam splitter to mix the fields from the two rings together. So in the output, we can have the one-dimensional CV cluster state in the degree of freedom of the spectral mode. To generate two-dimensional CV cluster state, we need to add two unbalanced Mach-Zehnder interferometers and a delay line. The delay line is for involving entanglement in time. In the output, we can have the two-dimensional CV cluster state in the degree of freedom of spectral mode multiplex temporal mode. To generate three-dimensional CV cluster state, we need four identical ring resonators and pump them all at different modes. We follow the same logic as we generate 1D and 2D CV cluster states. You use beam splitters and delay lines to form a 3D cluster state in the output of this layout. This 3D cluster state is in the degree of freedom of spectral mode multiplex temporal mode. From this layout, we notice that in stage 2, we can generate one-dimensional CV cluster state. In stage 3, we can generate 2D CV cluster state. So by tuning the electrodes here in this layout, we can programmably generate 3D, 2D, and 1D CV cluster state in the output. Also, we can make our quantum computing protocol to be fault-tolerant by injecting a highly non-Gaussian state called GKP state. There are some papers which talk about how to use GKP state to do the quantum error correction. This slide shows our current experimental progress. So far in our lab, we can fabricate a ring resonator and coat it with the electrode. The electrode is for shifting the resonant frequency of the ring to our desired value. The ring can have very high intrinsic quality factor, which is about 10 to the 7th. Also, we can fabricate the beam splitter and the delay line. In other words, so far in our lab, we have the capability to fabricate all the necessary components to generate CV cluster state and optical soliton. This slide shows an overall summary of our quantum computing architecture. We fabricate two sets of ring resonators on the chip. The first set of ring is for generating CV cluster state. The second ring is for generating optical soliton. We send a pump field to the two sets of rings, and after the optical soliton is generated, it is processed by the classical processing circuit and mixed with the CV cluster state by beam splitter to the WDM. WDM will spread out all the spectral modes to the detector array and do the measurements here. After that, we do the feed forward to determine the basis of next run. We thank all the authors who made the contributions to this study. Also, we thank Rafael Alexander, who is in the University of New Mexico, for thorough discussion. This concludes my presentation. Thank you.